For today, lecture 19. Going to look at some more factor group examples and some proofs related to factor groups. Again, factor groups are also called quotient groups. Then 19b, I'm sure we'll talk more about factor groups and probably proofs, and get started on internal direct products. We have an exam that on the syllabus is scheduled for next week. I put Friday of next week, question mark, because I am open to changing it if that's a bad day overall. Could be Friday, April 6th, or perhaps the next Monday, April 9th.
Let's do it. Fridays.
You like Friday? Other people agree? Okay, so we're going to plan on the exam being Friday, April 6th, so we have today. And next Wednesday, as far as what we meet, when we meet before next Friday, I do want to make an extra video. I'm aiming for tomorrow sometime. For extra content, not that you'll get extra homework, but extra content to help prep you for the exam, to help really make this an exam that gets through chapter 10. We're currently in chapter 9, and that will still be the case. The entire lecture today will be in chapter 9. So with my extra lecture that I make probably tomorrow, I'm going to start chapter 10, finish up chapter 9, and start chapter 10 in that lecture. I'm hoping that it'll be just one video and hopefully maybe less than an hour long, maybe 50 minutes or something like that. We'll start talking about chapter 10, also finishing up chapter 9. Next Wednesday then, we'll finish up chapter 10 as well as reviewing for the exam. The majority of the chapter 6 through 10. Chapter 6 was on isomorphisms. I probably should have written chapter 5 through 10. I mean, we did have permutations on the last exam, but I think I want to still emphasize that. But there could be some things from earlier chapters. Things are cumulative here. In particular, I'm thinking of modular arithmetic, subgroup tests, cyclic groups, examples of groups and subgroups, like, for example, centers of groups. Should be things that you know. Now, these ideas do, of course, come up in later chapters, chapters 5 through 10. So maybe knowing these means you wouldn't necessarily have to state a definition related to them or a theorem statement, but you might need to use it for some proof whose main content is chapters 5 through 10. Okay. If there's any pure cyclic group problem, for example, which I'm not ruling out, I'd probably tell you after I write the exam. Okay, so that's the plan. Remind you again quickly what a normal subgroup is. A subgroup H is normal in G, or is a normal subgroup of G if every left coset is a right coset. For any A in G, AH equals HA. That doesn't mean G is abelian. This can happen even when G is not abelian. In other words, the left coset of H in G containing A equals the right coset of H in G containing A. It's denoted by, and in my rush today, I had a real hectic morning. Our car was in the shop. My wife had to take me and my daughter to school. And I was up here trying to write a bunch of things on the board ahead of time, and the computer wasn't starting up. Anyway, I didn't have time to fix this. On a Mac, oops, this comes up with this symbolism, with the little triangle there. Transferring to the PC, it omits it for some reason. And on this particular PC, I was not able to fix it. I usually am able to fix it before class on a different PC, but I didn't have time this morning. Anyway, it's denoted by this symbolism. H is a normal subgroup of G. Comes up on another slide as well. Evidently, this definition holds out the possibility of it not being transitive, and I will say that that is the case. the normal subgroup idea is not a transitive relation. And that's brought up in an exercise. I forget if it's chapter 9 or chapter 10. I'm not going to take the time to search through these exercises to remember which one it is. But that is the case. There are examples where H is a normal subgroup of some subgroup K, and K is a normal subgroup of G, but H is not a normal subgroup of G. That does happen. There are examples of it. Okay. I think, in fact, the example can work in D4, which is what these Cayley tables are related to. And I think if I recall correctly, this might be wrong. If H is the cyclic subgroup generated by R180, and K is not a cyclic subgroup, but contains R0 and R180, it's this particular subgroup, it's not cyclic. H is normal in K, and K is normal in G, but, oh no, that's wrong. Sorry. I think it's this one here instead. H is normal in K, and K is normal in G, but H is not normal in G. I did not want to have what I originally had because that's actually the center of the group. And centers are always normal. So yes, this possibility can become an actuality. I'm going to skip over the normal subgroup test. I want to come to these examples of factor groups. So again, quickly, what is a factor or quotient group? As a set, it's the collection of all left cosets of H and G. The elements of the factor group are cosets. The elements of the set are sets. This is a set of sets. But groups are more than just sets. They also have a multiplication, binary operation. And looks like the PC didn't show it here. Oh no, okay, here we go. As a set, G mod H, this factor group, is a collection of all left cosets. The elements are of this form as A arranged over G. And yes, here is how you define the multiplication. It is good to think about examples first before we do proofs, and that's what we will do today. Let's look at what's on the board here. Fact. So what do we have on the board here? I've got two complete Cayley tables and two partial Cayley tables. We're going to look for patterns here. So this is just a copy of what's on page 33. So we are talking about D4 here. Symmetries of a square, right? D4, it's got 8 elements in it, 4 rotations. We're thinking of the identity element as a rotation. And 4 reflections, H, V, D, and D prime. H was a reflection across the horizontal. V was a reflection across the vertical. D was a reflection across this main diagonal, and D prime was a reflection across that off diagonal, so to speak, thinking in terms of matrices, terminology for matrices. And here again is the Cayley table from page 33. Maybe something stood out to you about this in the past when you looked at this. Did you notice that this part contains only rotations, as does this part? And the other two parts contain only reflections. If you identify the collection of rotations with this subgroup, which is part of the factor group of D4 mod by the cyclic subgroup R90, it's got 2 elements because we have 8 elements in there and 4 elements in there. 8 divided by 4 is 2. What are those 2 elements? One of them is the subgroup itself, thought of as a coset. And another one is, well, I could write it like this. Say, for example, H R90. The factor group has two elements. It's got to be isomorphic to Z2. This is its Cayley table if you focus on groups. That's a pun I didn't mean to say. If you focus on collections. Thinking again as all four of these elements as representing this one element of the factor group. And the other set of four elements, the reflections, as representing the other coset, the other element of the factor group. What we really have here is a Cayley table for Z2. This is isomorphic to that. Isomorphic to the Cayley table for Z2. You see it? This thing is acting like the identity, as it should in the factor group. The identity's there and there, that's like the 0 there and there. The non-identity element is this collection, it's this coset. It shows up here and here in this Cayley table. It's acting like the 1 here and here. How about another example? Here I'm taking K, the subgroup, to be the cyclic subgroup generated by R180 instead of R90. This has got order 2 now. Here are the distinct left cosets. This K being also the same as the center of D4 is normal in D4. And if you regroup the elements in the Cayley table to match what the cosets are, you can reinterpret the Cayley table as a new Cayley table for the factor group. D4 mod K. Notice that R0 and R180 are going together. R90 and R270 are going together. That's this coset. V and H are going together. I've reordered the elements here. That's that coset. And DK is represented by these two elements. I group those together. Now look at the substructure of the Cayley table here, or the group structure, you might say. Think in terms of these 2x2 submatrices, if you will. We've got a new Cayley table that really is the Cayley table for the factor group. Whenever you have R0 and R180 together, that represents the identity coset. You see it here, 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 and there. That's the identity element of the factor group. Watch where I point again. See it here, 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 and here. Along the main diagonal of this factor group, which is going to have 4 elements, every element is its own inverse. This is not isomorphic to Z4, it's not cyclic. This is going to be isomorphic to the external direct product of Z2 with itself. All non-identity elements have order 2. Because the identity element of the factor group, this coset, is showing up along the main diagonal. You square these elements, you get back to where you started. You get back to the identity, I should say. For example, if I square this coset, by the definition of coset multiplication, that's this, but D squared is R0, and R0 gets sucked into K. I did practice my sucking last night some, but I didn't practice it before class. Dare I try? Oh, that's not loud enough. That's better. That's what I meant to do. R0 gets sucked into K. This is K. That's the identity. What happens if we square that left coset? R90 squared is R180, but hey, R180 is in K. It gets sucked into K. Property of cosets, right? AH equals H. A gets sucked into H if and only if A is an element of H. What is, as another example, what is this coset times this coset? By the definition of coset multiplication, it's VD times H, but what is V times D? V composed with D is R270. This is the same as R270 H, the left coset containing R270. Does that really happen? When I take this element here, these two elements being thought of as one element, and compose it with this element, I do get a coset that contains R270. Also contains R90. I could also represent this as R90 H. Do you get what I'm saying here? As long as you reorder the elements along the side and the top of the Cayley table in the appropriate way for a given normal subgroup, you can see the factor group. You can see the Cayley table for the factor group. This particular subgroup is not normal in D4, so evidently that means something goes wrong when I try to do the same thing. And that indeed is what happens. Something does go wrong. So I tried grouping together the cosets, the distinct left cosets, that are listed there and shown in this way on the Cayley table. And certainly when you compose these things with the identity, it seems like nothing's necessarily wrong at first. It's only when you get into more details that things become wrong, so to speak. Let me compute H composed with R90. I'll look over at this one, what I'm used to. H composed with R90 is D. And H composed with D prime, H composed with D prime is R270. And if I was going to try this breaking the original Cayley table up into submatrices, so to speak, that correspond to the cosets, right away I have a problem. Those four elements do not constitute a coset. In particular, they're not this coset. That shouldn't be surprising if you think about it. D4 is non-Abelian. These cosets all have two elements, one of which is always the coset representative. I could also represent this coset as a right coset, or I could try to at least. I could wonder, is this coset the same as this right coset? Is that left coset the same as this right coset? They both contain R90, but the other element is not the same, which again shouldn't be surprising because D4 is non-Abelian. What would the other element be? It would be H times R90. So look here, H times R90 is D. These are not equal. Again, this shouldn't be surprising. K is not normal. In fact, I mentioned this before, I'll mention it again. Anytime you have a non-Abelian group, and you've got a subgroup of order 2 that's not a subset of the center, then the subgroup will not be normal. Say that again. Anytime you have a non-Abelian group, so the center is not the whole group, something smaller, and you've got a subgroup of order 2 generated by an element of order 2, that's not a subgroup of the center. So these elements don't commute. That second element that's not the identity doesn't commute with everything. It cannot be a normal subgroup. I hope that makes sense. Again, this is a subgroup of order 2. One of the elements in this coset has to match, but the other one won't match for some element that goes in front there. Because this is not a subset of the center. There's at least one element in there that doesn't compute with everything in the group. I'm not going to complete the Cayley table for this example, but this is a subgroup of D4 that does turn out to be normal in D4. And you could give a reason for that based on what I said last time as well. It's because this has index 2. D4 has 8 elements. This has 4 elements. 8 divided by 4 is 2. The factor group has 2 elements. The subgroup itself and this coset. Therefore, if I do this breaking up of the Cayley table in the way that you see here into collections like this, I should get a valid Cayley table. I'm not going to fill in the whole Cayley table, but let's just fill in this subpart here. All the elements that I should get here should match R90, R270, D prime, or D. Let's see if that happens. So looking back over there, so I've got to kind of go back and forth here. Why don't you first move the camera over here, and so people watching the video can pause it and maybe write that down or something, or look on page 33. We're going to calculate, for example, composing the rotations is easy. R80 composed with R270 is R90 is R270. R180 composed with R270 is going to be R90. R180 composed with D prime and D. Composing with D prime, you get D. Composing with D, you get D prime. What about H composed with these things? And looking over here when I do the composition, what about H composed with R90 and R270? H composed with R90 and R270 gives D and D prime in that order. V composed with R90 and R270 in the same order gives D prime and D. How about H composed with D prime and D? H composed with D prime and D first gives R270, then gives R90. And when you compose V with these, you're going to get R90 and R270 in the other order. And once again, like I said, you see that the elements in this block of the matrix are the same as the elements in this coset. And you get the same thing down here. And you get the identity for the factor group here and here. You get this coset, which is the subgroup itself. This would be K itself. This is isomorphic, this factor group, to Z2. All right, what about proofs related to factor groups? First thing we should do is verify that the factor group really is a group. And the hardest part of that proof is showing the operation is well defined. Let's do it over here. What does that mean? It means if you've got two different coset representatives for each coset that is being multiplied, you should get the same thing in the end. If these two facts are true, this should imply that ABH equals A prime B prime H. Does that make sense? Why you have to do that? Because cosets can have different representatives. You can have different things in front of them for left cosets and to the right of them for right cosets. By the way, we could have defined factor groups in terms of right cosets instead of left cosets, using left cosets as arbitrary. H is normal, the left cosets and the right cosets are going to be the same anyway. And that, in fact, is part of the proof. We need to assume H is normal in G. Assuming H is normal in G. That's the importance of the normality, is that it will make this operation well defined. What's the proof of that? Here's the way the book does it. Since A prime is in A prime H, I'm not going to write sentences here, but I'll outline the proof with ideas here and listen carefully to what I say. A prime is in the left coset of H and G containing A prime. It's A prime times E, and E is in H. But because I'm assuming A prime H equals AH, I can also say A prime is in there. That means there exists, oh, call it, say, H1 in capital H, such that A prime equals A times H1. This is really important. Should I say that again? Take this element A prime. It is in the left coset of H and G containing A prime because it's A prime times E. I'm assuming that left coset equals this left coset for some other element A. So A prime is in this left coset. What does that mean? It means it's the product of little a times something in capital H. There exists something in capital H where this is true. And I can write something similar with B prime. B prime is in this, which happens to equal this. So there would exist some other element of H, call it H2, such that B prime equals B times H2. That's a fundamental thing to understand about what's going on here when we're making these assumptions. By the way, if you understand this well, you can just really pretty much just jump to these two facts and you don't even have to write this book. You can just say, because of these equations, these things are true. But when you're first learning it, it's probably beneficial to write this stuff here first. What's the significance of that? What is our goal? Our goal, again, is to show that this equality is true. So now you're working on some scratch paper. You just do some algebra and see if it works out. Maybe start with the right side of that equation that you're trying to show is true. Write down A prime B prime H. Would make sense based on what we've already said to go ahead and replace A prime with AH1 and go ahead and replace B prime with BH2 and see if you can figure out whether that can be simplified or not, perhaps. You know, you're looking at this and saying, boy, if I could get rid of the H1 and the H2, then I guess I'd be done. Can you get rid of the H1 and the H2? Well, H2 gets sucked into capital H because it's in capital H. I'm still not doing a very good job. I need more practice. Again, don't make sucking sounds during the test, okay? H2 is in capital H, so it gets sucked into it. Capital H absorbs it, is another way to view it. Now what do we do with this? The H1 is not next to the capital H. Can't get sucked in. Until we realize, hey, wait a minute, I haven't used the normality yet. That must be relevant. Otherwise, why would I assume it? How can I use that here? Well, let me put parentheses in there for emphasis. You don't have to put parentheses in there. In fact, the book doesn't. But just for emphasis, that's a left coset of H and G containing B. It equals, by normality, the right coset of H and G containing B. I could switch around the H and the B. Like that. Haha, now we got it, don't we? Now the H1 is next to the capital H. It gets sucked in. I'll go ahead and put parentheses here just for emphasis. We get that. We got rid of the H's. But we're still not quite there. Well, use normality again. That right coset is the same as this left coset, and that's the same as this. Showing a couple extra steps there really for emphasis. So that's the book's proof of the well-defined fact. I wanted to do another proof of the same fact, using the fact that something like this is true if and only if, for example, A inverse A prime is in H. That was a property of cosets. Watch where I point again and listen to what I say. There was a property of cosets that said this being true is equivalent to this being true, which, by the way, is equivalent also to this being true. You can put them in either order as long as you put the one with the inverse on the left. Same kind of thing would hold with this equality, and same kind of thing would hold with the equality that you're trying to show. So ultimately, to show this with the other method that I'm hinting at here, you'd ultimately want to show that, for example, AB inverse times A prime B prime is in H. That's what you would want to show with the other method, to show it's well defined. For sake of time, I would encourage you to try that as an exercise on your own. Use the fact that this equality is equivalent to, say, this, and this equality would be equivalent to something similar involving B and B prime, and try to show that this is true based on those facts. That would prove the same thing. It's based on properties of cosets. Okay. But I think we better stop for the moment and take the quiz.